Hi, my name is Michał Dreziński, and I will be talking about solving dense linear systems faster than via preconditioning. This is joint work with my student, Jiaming, and we're at the University of Michigan. So our overall task can be stated very simply. Given a matrix A and a vector B, solve the linear system AX equals B, solve for X, right? And we're going to make a further simplifying assumption for this talk where the matrix A is a square n by n invertible matrix. Now, those are assumptions are not needed for any of our algorithms, but we're going to do that for this talk. So naturally, the task of solving a linear system has very broad applications across many domains, from statistical inference to partial differential equations. And in many of these cases, it is the actual one of the main bottlenecks in computational bottlenecks in these domains. So naturally, it's an important, well-motivated problem. So it's natural to ask, what is the cost of solving an n by n linear system? And perhaps because it is applicable in so many different domains, the answer really depends, right? It depends on many factors, including the sparsity of the matrix, the spectral profile of the matrix, whether it has some domain-specific properties like a graph Laplacian matrix, for example, and many others, right? But we're still going to try to, sort of provide a general context for the complexity of solving linear systems. So, oversimplifying things considerably, we can distinguish maybe two classes of methods for solving linear systems. One of them we're going to call direct methods, where the idea essentially is to compute either implicitly or explicitly the inverse of the matrix A, and which thereby immediately allows us to solve the linear system. And so that can be done in various ways via Gaussian elimination or various decompositions, matrix decompositions of A. And thanks to classical reductions to matrix multiplication, we can solve this. We can do this in time big O of n to the omega, where omega is the matrix multiplication exponent. So for classical matrix multiplication, that would be 3, so n cubed. But for the fast matrix multiplication, that would be currently approximately 2.37. Okay, so that's good, but naturally that's still much slower than linear in the size of the inputs. So, so we would, we'd like to do better than that. So the other class of methods are iterative methods, which gradually refine an estimate to the solution of the problem, right, as it converges to that true solution. So the advantage here is that each iteration here is more efficient, right? For example, for conjugate gradient, each iteration is costs n squared time. But the rate of this convergence to the optimum is really dependent on the spectral properties of the matrix A, right? And so this can be, so one simple way to express this is via the condition number, which is the ratio between the largest and the smallest singular values of A. And so that gives rise to the time complexity, which we can express easily as n squared times the condition number of A times log of the desired precision we want to solve the problem to. Okay, so that is fine, but of course there are several downsides here. Number one would be that the condition number is by itself a fairly crude metric for expressing the convergence behavior of iterative methods, right? And also, of course, it makes it quite difficult to compare the time complexities between iterative and direct methods, right? Because one class of methods depends on this condition number, on the spectral properties of the matrix, and the other one does not. So kind of the overarching motivation for our work is the question of can we parameterize the problem in some way to capture the trade-offs between direct and iterative methods, kind of unifying the two complexity perspectives. So of course, this can be done in a number of ways, right? And we're going to propose one way to do it. But clearly, it will require looking more closely at the spectrum, the single value spectrum of the matrix A, right? So let's take a look at that. So here we're showing the spectral decay, right, which is basically the sequence of decreasing singular values of the matrix A from the largest sigma 1 to the smallest sigma n. The ratio of those is the condition number kappa. And of course, the condition, this kappa, to some extent, it describes how ill-conditioned this spectrum of the matrix A is, right? But even if kappa is very large, that doesn't necessarily mean that the whole spectrum of A is ill-conditioned, right? It could be that only a small part of the spectrum is very ill-conditioned, and then the remaining part of the spectrum is quite well-conditioned, right? As in this example, where the kind of the ill-conditionedness of the spectrum is really due to a relatively small number of the singular values. So, at a high level, this is going to be our strategy of, thinking about the problem, which is to separate the spectrum of A into the ill-conditioned part, which will favor the direct methods for solving linear systems, and the well-conditioned part, which will favor the iterative methods. So this leads us to the following problem formulation, which we call as solving linear systems with k-large singular values, or the k-large singular value problem. So here we ask, what is the complexity of solving an n by n linear system, Ax equals b, with at most k singular values larger than some constant times the smallest one? We can also replace the big O of 1 with another parameter, the condition number of the tail, but let's leave that for later. Okay, so the nice thing about this problem is, first of all, well, it is quite general in the sense that any linear system has some value of k for which there's k large singular values. It could be 0 if the system is well conditioned, or it could be n if the whole spectrum is extremely ill conditioned, right? And so in the former case, we would probably prefer iterative methods to solve it. And in the latter case, we'd prefer direct methods. Okay, so naturally, there's various other ways we could formulate a problem like this, but the choice of distinguishing the top part of the spectrum as the ill-conditioned part is actually quite well motivated by linear systems that arise in many practical applications, particularly relating to data science domains, where the matrix A, is based on some sort of a data matrix, which is often composed of some low-dimensional signal information and distorted by some noise, either coming from the measurement or some randomized rounding effects and so on. And this noise typically has the effect of so-called implicit regularization, meaning that it flattens out the tail of the spectrum of the matrix, which exactly fits to our problem. And so, and of course, not to mention the explicit regularization that is often applied to linear system tasks in domains such as machine learning, statistics, and optimization, which also result in linear systems that fit into this k-large singular value setting. Okay, so what is the best we could hope for algorithmically for solving this problem? Well, the ideal case is if the linear system is kind of already split up into two parts. the part that is ill-conditioned and the part that is well-conditioned. So here we would have this as a block diagonal matrix A, right? So there's a K by K block, which is arbitrary or ill-conditioned. And there's the second bigger block, which is well-conditioned, right? So to solve this linear system, we effectively have to solve both the ill-conditioned and the well-conditioned system, right? So that leads us to a conditional lower bound on the complexity of this problem of omega of n squared plus k to the omega time. So now let's ask, okay, so what are the algorithmic approaches we could use to actually try to achieve this time complexity? Well, the textbook strategy would be preconditioning, right? So how can we, so what is preconditioning, first of all, right? So a preconditioner is you can think of it as a matrix data structure, M, with two properties. First, we can quickly solve the linear system associated with M, for example, using a direct method. And second, computing, the matrix AM inverse gives rise to a well-conditioned system for which an iterative method converges fast. So this already, this approach of preconditioning already in a way, allows us to, get the benefits of both direct and iterative methods to some extent. Okay, so how should we precondition a linear system with k-large singular values? Well, let's start with something obvious, which is that if we already had a singular value decomposition, a full singular value decomposition of the matrix A, meaning the matrices U, sigma, and V transpose, right? Left, right singular vectors and the singular values, then this, viewed as a data structure would essentially be the ideal preconditioner, because we can, given the singular value decomposition, we can invert this easily, and the, preconditioning with this matrix, of course, is sort of the ideal preconditioning. But of course, that is kind of defeats the purpose of preconditioning, because that already solves the problem, and it already costs the go of n to the omega to do this. So instead, a natural thing to do is to do a partial singular value decomposition, right? So in this case, we would try to approximate the top k part of the spectrum, which incidentally is precisely where the ill-conditionedness lies in the spectrum of the matrix arising in our problem, right? And so it turns out we can do this effectively using an approach often called randomized top KSVD, which a very classical approach involves using a so-called randomized block power method to approximate the top part of the spectrum of A, and then use this approximate top KSVD to build. We can use it to build a cheap preconditioner data structure that will be easy to invert, and that will effectively precondition the top part of the spectrum of the matrix. So what does this give us for our problem? Well, so this is recall our problem, right? Solve an n by n linear system with k-large singular values. Recall the lower bound we have. Well, what does lowering preconditioning give us? Well, naturally, the cost of this procedure is the cost of preconditioning, and then the cost of the iterative solver, right? So unfortunately, here the cost of the preconditioning is the dominant cost, as we see, right? So this is where does this come from? Well, the main step in the lowering preconditioning is performing the block power method, which requires several steps of a matrix multiplication of an n by n matrix by an n by k matrix. So here I've written this as n squared k to the omega minus 2. So for classical multiplication, this would just be n squared k. For fast multiplication, this can be still further sped up. But regardless, it will still be the dominant cost of the whole operation, so slower than the solving part. And this is because we require essentially a high quality low rank approximation to get a good enough preconditioner, right? The condition requires sort of a spectral norm low rank approximation condition given here. Okay, so let's look at the complexity diagram for the problem to see how things play out here. Okay, so basically we're looking at how the time complexity of the problem changes with k, right? So, and this is all done in log scale. So k equals n to the power theta, and we plot theta between 0 and 1 on the x-axis. And then on the y-axis, we have the complexity n to the power beta, and we plot beta. So clearly n squared at the bottom is the best we could hope for. N to the omega at the top is kind of the worst we could hope for. And in the red, we have the lower bound, which basically says, the lower bound says we should hope to be able to get the best n squared time up to a certain value of k when k to the omega has to dominate the cost, right? Now, preconditioning, as we've described it, actually behaves quite differently, meaning that the time complexity essentially increases as we increase k. The exponent of the time complexity increases kind of linearly as we increase k from 0 to 1, right? Now, this can be partially addressed with fast rectangular matrix multiplication, which has this sort of short phase of not paying for increasing k. But even then, we have this large area, this gray shaded area, where there's a gap between the upper bound and lower bound. Okay, so the main result of our work was the following algorithmic result for solving an n by n system with scalar singular values, showing that we can do this in roughly n squared plus nk to the omega minus 1 time. And interestingly, this is achieved by an entirely different approach. So not using low rank preconditioning, but rather using a stochastic solver. So an iterative method that uses stochasticity in each iteration based on the framework known as sketch and project. I will talk about that a little bit more in a second. So what's remarkable about this result is that you see two terms. You see the n squared term, which is necessary, and the nk to the omega minus 1 term, right? But importantly, for a wide range of the values of k, so up to big O of n to the 0.73, the second term is dominated by the first term, meaning that overall runtime is nearly linear at O tilde of n squared. And so this is, by the way, the exponents are coming from fast matrix multiplication, but even under classical matrix multiplication, this result gives a significant improvement, right? Up to k equal of square root of n, we still have linear time with classical matrix multiplication. And so, in fact, this improves over the low rank preconditioning in essentially the whole range of the values of k where we saw it being suboptimal, right? So let's look at the diagram again. This is the same diagram as before. We have the triangular gray shaded area. And as we include the new result, we see that it essentially covers up most of that gray area, but not all of it, right? Because we haven't matched the lower bound, right? And because nk to the omega minus 1 is still worse than k to the omega, right? But now we can achieve linear time, nearly linear time algorithm with k up to n to the 0.73, right? So a very nice improvement, although the gap is still there. I will come back to that at the end as well. So how can we achieve this? Well, since I don't have a lot of time, I will just mention this briefly. But the main technique that allows us to achieve this result is called sketch and project. So this is an iterative method, right? So it constructs a sequence of iterates x0, x1, x2, xt, xt plus 1. and which aim to converge to the solution X star, right? And so how do we update those iterates? Well, first we sample a random matrix, random k by n matrix S, right? Which is called a sketching matrix, hence the sketch. And then we project xt onto the solutions of a smaller linear system, so-called sketched linear system, SAX equals SB, right? So this is a highly underdetermined linear system, right? The matrix is very wide now, much smaller. And so it has many solutions, and we project our current iterate onto the set of these solutions, right? And then in the next iteration, we resample the matrix S and project again, and over and over. So it's actually a relatively simple algorithm. Of course, the question is, how do we sample the random matrix S, and how do we analyze the convergence of that algorithm? Well, fortunately, there's a quite simple and elegant convergence guarantee for sketch and project, which is given here, right? So basically it says that in expectation, the distance from the optimum in each iteration reduces at a linear rate, which is described by this quantity in blue. So what is this quantity? This is the smallest eigenvalue of the expectation of a random matrix P. And this random matrix P is simply the projection matrix corresponding to the projection step we're doing, right? So what is this quantity? Well, that's the hard part. It turns out, even though there has been very extensive work on sketch and project, various extensions and specializations of this method since it was introduced by Gauer and Richtreich back in 2015, the main challenge has been actually characterizing the convergence rate in a way that would somehow explicitly correspond to the properties of the matrix A itself, right? And in particular, doing this for a sketching method that is actually efficient enough to get complexity improvements. So this is essentially our contribution, right? First, to actually analyze this smallest eigenvalue, this quantity, and to do this for a fast sketching method as well. So I won't have time to get into the details of the analysis, but I will just point out that it crucially relies on two techniques from randomized linear algebra, which interestingly are not usually seen together in one place. And those techniques are, on one hand, determinant of point processes, which is a non-IAD subsampling method, and randomized Hadamard transforms. So, okay, to conclude, in this work, we consider the problem of solving an n by n linear system with k large singular values, right? Which was motivated by trying to essentially unify two complexity perspectives, sort of interpolating between direct and iterative methods for solving linear systems, plus being motivated by applications to linear systems for data science domains. We showed an algorithmic approach for this problem, which gets the time complexity n squared plus nk3 omega minus 1. Interestingly, using a stochastic solver, right? Stochastic iterative solver, as opposed to the more standard approach to this, which would be low-rank preconditioning. We also have additional results in the paper for sparse PSD linear systems and least squares regression. I will also briefly mention that we could sort of take a more fine-grained look at the problem by replacing the big O in the problem formulation with a specific parameter, which we would call tail condition number, kappa k. And we've done that in a follow-up work that you can take a look at as well. And then finally, let me close with returning to the remaining open problem, which is closing the complexity gap that shows up in this diagram with this gray area, gray triangle, right? Which was not entirely closed by our work in this paper. Now we have actually since made some progress on this by revisiting the approach of low-rank preconditioning, by developing this idea of multi-level sketch preconditioning. But that's still, so you can also check out that work, but that still doesn't entirely close the complexity gap. And so the open problem still remains. I think it's very interesting. So that's our work. Thank you for your attention.